Good morning, students. I hope I'm audible to all of you. Please respond through the chat box whether I'm audible or not. Okay, so very good morning to all of you. Now, those who are already present, please start giving your attendance in the chat box. Attendance format should be enrollment number, full name, stream, section, roll number. Enrollment number, full name, stream, section, roll number. So those who are already present, please start giving your attendance while others join in. And then we will start. We'll start in next 2-3 minutes or 5 minutes. Okay. Okay, so while others are joining in, we will discuss something from the previous class and we'll continue that thing today. Now, in the previous class, we had ended our discussion with the different type of anomalies that we find in our database management system. So what basically we do is when we create a database, we create a lot of tables. So tables are what? The row column structures. Now, already you have learned the relational algebra, so you have the idea that what exactly we do, how we join the tables and those things. Roughly, you have the idea. Now, when we have tables, what are the problems that we can face? So generally, we categorize those problems as three types. So we call them as anomalies. Anomalies means these type of problems will not appear in every situation. Means, suppose I call the first one as the insertion anomaly. Insertion anomaly. So suppose if I have a table where I am trying to maintain student data, right? I have given this example previous day also. So if I have a table where suppose student ID, student name, student department, suppose the department HOD. These things we are trying to maintain. So suppose student ID, I have 5 students. Name is suppose X, Y, Z, P, Q, any random names. Now suppose 1, 3 and 4, these students are studying in CS department. Number 2 is studying in EC department and suppose number 5 is studying in biotech department. Okay. HOD will be for CSE, there will be a constant HOD. So suppose ABC is the HOD of CSE department. Right? Suppose PQR is the HOD of ECE and suppose STB is the HOD of biotech department. This is my situation. Now, when you are trying to insert a data, suppose a new data about a student who is not right now in the table, that means who is not enrolled here. So how you will insert? You have to insert that student by mentioning their department as well, because this is a common table. So whenever you are trying to insert a student, the department should be mentioned. But here see, only 3 departments are present: CS, ECE and biotech. Now, if suppose I want to insert a student with an electrical stream, that is not possible here in the table. Now, you can say that, yes, I can write insert query, like insert into table name data, in bracket, whatever columns you have, you will give the data. You can do that, but if I try to insert a student by mentioning the department, right, that insert into this where S department is equals to electrical. So in that case, I cannot do it in this particular table. Similarly, if we go for deletion anomaly, now again, this type of insertion anomaly will not happen if I try to insert a student in CS, because CS is already present. So if I try to insert a student in CS, then insertion anomaly will not occur. Right? So anomaly we are calling it, not a problem, because problem will happen every time when you try to insert any data. But anomaly is not like that. Anomaly may happen in certain cases. Next one, suppose deletion anomaly. Now, what is deletion anomaly? If suppose you are trying to delete some data and because of that, the total information about the stream is getting deleted. Okay. Now see, you have only one existence of the biotech department in your table. Similarly, same thing goes for ECE as well. You have only one existence. Suppose this student Q is trying to leave the university. That may happen, that student has got some other chance in suppose some other university or something else that student is planning to do. So that person is trying to leave the university. So what you have to do, you have to delete this particular row. Now, while you are deleting this particular row, the information about the biotech's HOD, the Department of Biotech and the HOD of Biotech STB is getting deleted. Once you delete this particular row, then what will happen? If you delete this particular row, then the biotech department's existence is also getting deleted from the table. From this table, biotech is not getting deleted from your university. But from this table, when you are looking at this table, you are not having any idea that whether biotech is existing, who is the HOD, those things are not available. Those informations are not available. So what is deletion anomaly then? For deleting one particular data, if the total information about some entity or some existence is getting deleted, then we call it as the deletion anomaly. Similarly, if you are trying to suppose delete X student who is belonging to CS department, then the department's data is not getting deleted. X can be deleted, this particular row can be deleted, but number 3 and number 4 are present. So CS department's HOD name ABC, that is present in your table. Fine, so this is deletion anomaly, not happening in every case, but in some cases it may happen. Okay. Next one, the third one is updation anomaly. Now, updation anomaly is what? If you have redundant occurrence of some data like CS, HOD is ABC, you are having 3 times. When you are trying to update this data, there may be some instances where the ABC, suppose ABC is getting changed to DEF. Okay, so HOD is getting changed for one string, ABC string, CS stream. ABC is getting altered as DEF. But as you have multiple occurrences of ABC, so everywhere you have to go and change for DEF. In some of the instances, this may be a problem where data may not be updated in every instance or every case. Fine, suppose here it is getting changed, here it is getting changed, but here ABC is not getting changed. Due to some problem, ABC is not getting changed. So in this particular case, as the data is redundant, CS is redundant, CS is redundant in 3 times in this particular table, right? So if this is the situation and any one of the data is not getting updated, we call it as the updation anomaly. So for that, if these are my problems, I have identified the problems. So what I will do, I will break my table into T1 and T2 where data redundancy is lesser. In T1, what I will have, in every table, I will have one primary key or any key which is trying to identify other columns. So in T1, I will have SID, SNAME. Along with that, I have to maintain that which student is studying in which stream. That is what the goal of this particular student table, right? So SID, SNAME and S department will remain in the first table. What are my attributes? SID, SNAME and S department, right? And in the second table, S department is trying to determine HOD. In the second table, there are 2 parts of the table. One part is this one, where student data is getting maintained, and one part is this one, where the department's data is getting maintained, right? So in the second part, I am trying to maintain the S department and the HOD. Okay. So this is my case where I am trying to break the table due to the problems. Now you come to the term, what is normalization, or why do we study normalization? These type of problem that we are studying right now, these type of problem, if getting occurred in your database, we will try to remove that. So for that, we are breaking this table. And this particular work is named as normalization. So we will try to identify a few problems. We have already studied functional dependencies. So depending upon those dependencies, we will try to remove we will try to remove these type of problems that occur every now and then in your table. Okay, now before going into normalization or normal forms that you hear every now and then, few terminologies we will study. We will just revise. The first one is functional dependency. That we have studied, we have practiced few problems. What is functional dependency? If I have a table T1 and in that I have columns A, B, C, suppose if I say A is functionally determining C, this is the representation A arrow C, A is functionally determining C. What it means? If there is any tuple, small t1 means tuple, in A is equals to another tuple in A. That means if you consider this as your table, this is your T1, this is your T2, this is your T3, this is your T4. So suppose A is having X here and in T2 also A is having X and here suppose Y and Z, and A is functionally determining C, then whenever A is repeating itself, C will repeat itself. So if this is my situation, then T1 of C has to be equals to T2 of C. And Y can be anything, Z can be anything. Okay, and B, suppose AB, BC, AC, and BA. Suppose anything. Okay, so what is functional dependency? If any particular column is functionally determining any other column or columns, then for every tuple of the determinant, the dependent will repeat itself. So what is determinant and what is dependent? This side is your determinant and this side is your dependent. So whenever the determinant is repeating itself, then the dependent will also repeat itself for those instances. This is functional dependency, right? If this is my situation, if this set of rules are applicable, then we can say that C is functionally determined by A. C is functionally determined by A. Similarly, one variable can determine more than one variables or more than one attributes at the same time. This you have already studied. Okay. Now, another thing you have studied, another two things you have studied. One is partial functional dependency. What is partial functional dependencies? Because you will require this in normalization. So I'm just doing a quick revision. Partial functional dependency means if you have a candidate key, suppose AB. AB is your candidate key. Your table is suppose T1 is having suppose A, B, C, and D. Now, what is partial dependency? If any non-prime attribute is getting determined by a subset of the candidate key, then we call it as the partial dependency. So if this is my only candidate key present, then what is my prime attribute? A and B. Prime attribute means a part of any candidate key present. So if you have only one candidate key, then this is your prime attribute. What is your non-prime attributes here? C and D. if you have any valid functional dependency on the table, as suppose B is trying to determine D. B is trying to determine D. That means any prime attribute, not a key, but a prime attribute is trying to determine a non-prime attribute. Any prime attribute, not a key, but a part of a key, is trying to determine a non-prime attribute, then we call that type of dependency as partial dependency. Okay. If I say that AB is determining D, that means this dependency does not have any problem. This is not partial, right? So this is not partial, this is a normal full dependency. But what is a partial dependency? If you have any attribute which is a part of a candidate key and it is trying to determine any non-prime attribute, then we call that as a partial dependency. Okay. Now with relation with this partial dependency, let us discuss FFD, fully functional dependency. Fully functional dependency. What is this? Suppose I have a table where I have S number, S name, suppose a status of your order or something, and the city. S1, S2, S3. In S name, suppose I have A, M, R. Okay. In status, I have, and in city, I have, suppose, Delhi, Pune, and Kolkata. A random table I have taken. Now, you can see here, S number and status. If I combine, what type of dependencies you can understand? S number is a primary key, you can see. So S number is determining, I can say, city. Again, status is also not repeating itself, so I can say status is also determining city. Also, if I combine S number and status together, this is also a unique type of ID which is determining city. So if I take this one as X and this one as Y, understand, if I take this total combination as X and this combination as Y, then a part of X, proper subset of X is also determining Y. What I can say is proper S number is a proper subset of X and status is also a proper subset of X. So proper subset of X is also able to determine Y. If this is the situation, then it is not an FFD. It is not fully functional dependent. Y is not fully functionally dependent on X. If this type of situation occurs, that is partial dependency occurs, then we will say that Y is not fully functional determined by X. So when I can say it is fully functional determined, suppose you take a table where you have S number, P number, and quantity, right? So in S number, you suppose have S1, S2, and S3. In P number, you have packaging number, suppose P2, and you have suppose P1. So in quantity, you can have anything 150, 100, 180, 200, 220, 200, right? So if this is your situation, you see S number, comma P number, this combination is always unique. S number and P number, this combination is always unique. Look at the table and understand. If I say S number, only S number is not unique. only P number is also not unique. Unique means it is not repeating itself. But if I combine S number and P number together, then this combination is unique. And as this is unique, I can say this is determining my quantity. So if this is my X and this is my Y, then none of the part of X, that means S number and P number, is functionally determining quantity. None of them is functionally determining quantity. See S number, where the repetition is occurring. This and this is repetition. So S2 and S3, they are different. That means S number is not determining quantity. Similarly, if I say P number and P number is having P1 here and P1 here. Suppose this is not P1, this is suppose P12. Okay, unique combination, or else P number is determining quantity, it will become. So P number is also unique in all the cases. So P number is also not determining your quantity. So if this is the case where none of the proper subset of X is trying to determine Y fully, then that means what? Quantity can only be determined when you have S number plus P number, right? So in this case, I can say Y is fully functionally determined by X. Understand what is full functional dependency and what is partial functional dependency. In a case where a part of your candidate key, S number and P number here together is forming a candidate key from the table. So if the total candidate key is trying to determine another attribute, which is the non-prime attribute, and none of the proper subsets of the candidate key can determine that non-prime attribute, then only we can say that it is a fully functional dependency. It is a fully functional dependency. Okay. Is this idea clear? What is partial and what is full? Is it clear? Clear to everyone? Is this idea clear to everyone? Okay. So next we will move to, can you please repeat the partial? Partial means, this one is partial. If your candidate key is S number comma status in the table, which is trying to determine city. City is a non-prime attribute and S number is a prime attribute, status is a prime attribute. Now as S number is able to determine city, that means a prime attribute is trying to determine a non-prime attribute, then it is named as partial dependency. So what is partial dependency? If a part of a candidate key, not full candidate key, but a part of a candidate key is also able to determine a non-prime attribute single-handedly, right? So that is named as a partial dependency, right? Like suppose your enrollment number, your name is trying to determine your marks, suppose. But your enrollment number alone is also capable of determining your marks. So that type of dependency is named as partial dependency. A part of a candidate key, that is a prime attribute, is trying to determine a non-prime attribute. We call that as a partial dependency. Okay. Next we will go to transitive dependency. Transitive dependency. What is a transitive dependency? If you have a situation where A is determining B and B is determining C, then we can say A is determining C transitively, right? Suppose enrollment number is determining name and name is determining grade or marks. So I can say enrollment number is determining marks. So this type of dependency is named as transitive dependency. So if suppose you want an example of transitive dependency, suppose you have the employee ID, name, and suppose department ID, right? Employee ID, name, and suppose department ID. Now, and also you have department name, right? Suppose in this particular table, employee ID is determining department ID and department ID is determining department name. That means we can say that employee ID is determining department name. So this type of dependency is named as transitive dependency. Transitive means, suppose it is a chain-like dependency. Chain-like dependency. Okay. So suppose you take another example of transitive dependency, like suppose you have movie ID, suppose list ID, list type means category, list means category, and suppose the buying price, okay, something. So here movie ID is determining the list ID and list ID is determining the list type. Suppose you take some example, then you may understand. Suppose movie ID 1, 2, 3. Suppose M1, M2, M3. Right? List ID is suppose L51, L55, and suppose L55. Okay. So whenever it is L51, it is a horror movie. Right? Genre of the movie. Type is L55 is suppose comedy, and this is also suppose comedy. Okay, and this is suppose 1,000 rupees. This is suppose 1,200, and this is suppose you say 1,500. Okay, so here I can say movie ID is trying to determine what type of movie it is, but based upon the list ID, right? So movie ID is determining list ID and list ID is determining list type. So in this case, if I just combine, then by movie ID also I can say what type of, what genre of movie this is. So this is named as transitive dependency. This type of dependency is named as, like some dependency which is going via, you can say via list ID, it is going to list type, right? So this is named as transitive dependency. Okay. Next, the concept that we have is multi-valued dependency. Multi-valued dependency. What is multi-valued dependency? There will be at least 3 attributes in a table. At least 3 attributes in a table to judge whether it is having a multi-valued dependency or not. Now, once I have 3 attributes, this is criteria number 1. Criteria number 2 is B and C, that is any 2 attributes are independent of each other. Independent of each other, right? And third one is both the independent attributes are carrying or are defining multiple facts about A, multiple facts or multiple ideas about the other attribute present. So I have minimum, I should have 3 attributes. It can be more than 3. If B and C, any 2 attributes present, are independent of each other and B and C both are carrying some multi-valued facts about A, then only I can say, if these 3 conditions are satisfying, then only I can say that A is multi-valued determinant of B and C. This is the symbol that we represent, double arrow of B and C, right? So suppose you take an example of very common example that you will find. Suppose bike model number is determining the manufacturing year and the color. So bike model number, suppose M 2001, M 2011, M 3001, M 3001, M 4006. Manufacturing year is suppose 2008, 2008, 2013, 2013, 2017. This is suppose white, black, white, black, white. Okay, understand the dependency first. See, the manufacturing year is 2008 here and 2008 here. That means in the year of 2008, 2 bike models were produced, right? That means what? If you consider this as your A, this as your B, and this as your C. So B is carrying multiple values about A. B is carrying multiple values about A. B is 2008, B is 2013, B is 2017, right? So this 2013, in the year of 2013, the bike model is same, but the colors are different. So what I can say, different colors, but same bike manufacturing year and same bike model number. Suppose you take the example of Swift Desire. So Swift Desires are getting produced in a 1 year. Millions of Swift Desires are getting produced, and everyone is not of same color. So one car Desire, different manufacturing year, some are common, some are different, but those who are having common manufacturing year also, like this, they are also always not same in color, they are also differing in color, right? So if this is your situation, then you can say that color and manufacturing year both are dependent on bike model. Once you say your bike model, then only we are able to determine that in which year it was produced and what was the color, right? So again, they are also different in number. That means in 1 year, only one bike was not produced, firstly. Second, for same bike model also, different years can be possible, and for same year, same manufacturing year, same manufacturing model number, your colors can be different. Like all Swift Desires are not of white color, and everyone is also not of, suppose, coffee color or like silver color or something like that, right? So they are differing in colors, differing in manufacturing years, but the model remains same. So if this is your situation, so what you will do, or what you can say, your model, your bike model is multi-valued determining the color, and your bike model is multi-valued determining the manufacturing year, right? If this is the case and you want to eliminate multi-valued dependency, you want to eliminate multi-valued dependency, then what you will do? You will form a T1 and T2 out of your, suppose T11 and T21. If your main table name is T1, if your main table name is T1, then you will divide it into T11 and T12. So what your T1 will have? Only one dependency will be present. Right? So this is how you can eliminate your multi-valued dependency. So these are few of the types of dependencies that you will require for your normalization. So these are the problem areas. Partial dependency, if it is present, then we need to eliminate. Transitive, if it is present, we need to eliminate. Multi-valued, if it is present, we will eliminate. Along with them, we need to remember the concept of keys. What is a super key? What is a candidate key? What is a primary key? Okay, so multiple times I have told this, we have practiced problems. And now we will move to the types of normalization. Okay, we will move to the types of normalization. Right? So first, we will start from first normal form, 1NF. NF stands for normal form. Okay. Multi-valued concept. Multi-valued concept means for any one column, even if the data is getting repeated, there can be multiple different occurrences of some other attribute in some other column. Okay. So in the previous example, we had the bike model, which was trying to determine the manufacturing year. Similarly, we will have another concept or another example we will learn when we learn the respective normal form. Okay. So first we'll go with first normal form. So this is the easiest. What points you have to remember? What question will be asked to you? Either it can be a form of question that what is 1NF, or how can we determine 1NF? This type of questions can be there. Or else a table will be given with a set of FDs, functional dependencies, and you have to determine that in which normal form it is. In which normal form it is present. Okay. So what is 1NF? There are few points. First is every cell will have atomic values. Atomic values in every cell. What is a cell? Cell means the intersection of a row and a column. That is a cell. Okay. I will give example. First, let us understand the points. If these points are satisfied, then we can say that a table is in 1NF. Next one, all column names are unique. All column names are unique. Third point, one column will have only one data type. Will have the values of only one data type. Right? So how can we give an example? Suppose I have employee ID, employee name, and employee contact. Suppose employee ID is employee name, suppose Akash, Kapil and Anurag, random names. Employee contact 1 2 3 4 5 2 5 1. So let me draw the table so that you can understand. So suppose Kapil's contact number is 1271 and Anurag's is 1155 and 2171. Right? So if this is my table, if this is my pattern of the table, then I will say that it is not in 1NF. This particular table is not in 1NF. Why? Every cell will have atomic values. Look at this cell and this cell. Are they atomic? Atomic means a single value, right? So multiple contact numbers of Akash and Anurag, so they are not in atomic values, right? So first condition is not satisfied, and hence we can say that it is not in 1NF. Fine. Next one, second column names are unique. Yes, column names are unique here. Employee ID, employee name, and employee contact. Every column will have similar data type. So here it is integer data in employee ID, varchar or character data in employee name, and in employee contact, again, it has got integer data, right? So there is no problem with column names. There is no problem with the column data types, but single values or atomic values must be present in every cell, and here the rule is getting violated. So if I want to normalize it to 1NF, how my table will look like? There will be no change in the table structure. In 1NF, there is no change in the table structure. But if you have different like multi-valued cells, multiple valued cells, not atomic, then you have to break them. So 111 Akash, and Akash's contact number was 1234 and 5251. 1234 5251 with an repetition of the values, right? Next one, 115 Kapil 1271, only one value. So 115 Kapil 1271. Next one, 127 Anurag with two phone numbers. So 127 Anurag phone numbers 1151 and 2171. 1151 and 2171. So no change in values, just we are breaking all the column, all the rows, so that every cell can have an atomic value, right? And if you say that if there is any situation where suppose the data types need to be changed, then that cannot be done here. There you can say that this table is not in 1NF because of this problem. So this value needs to be changed. Suppose this employee ID was S1. So that is not allowed. This is not allowed. So you can write just 1, but S1 is not allowed because it is becoming varchar. It is not integer anymore. Right? So these are the 1NF criteria. So if a table is in 1NF, then we have to maintain these three criteria. First one, every cell should have only one value. every column name must be unique from each other, and every column must have only one data type value. Okay, if these three criteria are matching, then we will say that your table is in 1NF. Okay, repetition is valid. Yes, repetition check is not being focused in 1NF. What he is trying to ask is, suppose employee ID is not unique in every case, right? So here employee ID may or may not be unique. That does not matter. In 1NF, we do not check those things, right? The names must be unique and the data should be atomic in every cell. This is 1NF. And generally we consider, suppose in question when you have a table and you have some functional dependencies given, then we generally consider that only by looking at the functional dependency, you cannot conclude whether the table is in 1NF or not. But basically in DBMS, whatever tables you store, everyone is in 1NF. We consider it like that. Okay, so if none of the normal forms are getting satisfied, then we go for 1NF. Okay, yes, this table is now in 1NF. This table is now in 1NF. Okay. Criteria, every cell. Cell means this is one cell. This is one cell. Cell means the intersection of a row and a column. That is one cell. Every cell should have atomic value. Atomic value means single value. If you have these type of two values, then that is not allowed in 1NF. Okay. All column names are unique from each other. Employee ID, this column name must not be repeated anywhere. Yes, you can have employee ID underscore name. That is also unique, but employee ID cannot be the name of two columns at the same time, right? And third one column must have the data of only one data type. Either employee ID, everyone should be integer, or everyone should be varchar. Employee name, everyone should be integer, everyone should be varchar, anything. Okay. Repetition part means what he was asking, one student was asking is, this employee ID, this is repeating, this is repeating. So is this allowed? Yes, this is allowed. There is no problem. We are not checking for any repetition in 1NF. We are not checking for any repetition. We are not checking for any functional dependencies in 1NF. Okay. Every functional dependency, whatever you want, if that is present, okay. Fine. Is 1NF clear? Again, I say, if a table is given, we will do problems today also. So if you see, if there is, suppose a table given, a table structure, not like this. If a table is given, and if that table is having only functional dependencies, then there is no scope of checking any 1NF criteria. There is no scope of checking any 1NF criteria. Okay. So if this is the situation and you are asked to verify whether the table is in 1NF or not, then please say that the table already present in a database management system is already in 1NF. You cannot check 1NF only with functional dependencies given. If the table structure is given like this, if this type of structure is given, then by visualization you can say that the table is not in 1NF. But if only functional dependencies are given, that is employee ID is determining employee name, employee ID is determining employee contact. If this is the dependencies that are given, then you cannot say whether the table is in 1NF or not. Okay, so we will do problems and there you will understand that how to check. So this is your 1NF. Very easy, the easiest of the lot. Next we go to second normal form. So there are just two criteria by which we can understand whether a table is in 2NF or not. First criteria is the relation R must be in 1NF. Must satisfy in 1NF because we are going high in higher order. So the lower order must be satisfied. That is, it must be in 1NF and no partial dependencies present. No partial dependencies must be present. So if partial dependency is present, then and there we will break the table. Okay. What is partial dependency? Any prime attribute trying to determine non-prime attribute. This is partial dependency we have learned just now, right? So any part of a candidate key trying to determine any non-prime attribute, we call it as the partial dependency. If this type of problem is occurring, then we must break the table. Okay, let us take one example. So these two are the rules. Now we will see how to satisfy the rules. Suppose teacher ID, subject, that is the teacher is teaching, and the teacher age, right? Suppose suppose not 17, 17, 25 and 43. Subject is suppose teacher ID with 17 ID is teaching, suppose chemistry and biology both. It can happen, one teacher can teach chemistry and biology both, there is no problem. 25 is teaching maths and 43 is teaching English, suppose, right? So the teacher with ID 17 is having age, suppose 35. Okay, whenever the teacher ID is 17, the age will be constant, right? If suppose my ID is 17, so my age will be constant. So whatever subjects I teach, my ID will be constant. So that is what here. 25 ID teacher is having suppose age 42 and 43 ID teacher is having suppose age of 32. This is my table, right? This is my table. Now you see, what is your candidate key here? Teacher ID itself is not the candidate key because teacher ID is having repetitions, right? So I can say teacher ID comma subject is my candidate key here, right? Teacher ID comma subject is my candidate key here. Teacher ID is having repetition, but if you combine teacher ID comma subject, then there is no repetition. 17 comma chemistry, 17 comma biology, 25 comma maths, 43 comma English. This is not having any repetition. So this is my candidate key. Now you see the teacher ID is straight away determining the teacher's age. Teacher ID is determining teacher's age. This is a valid functional dependency. Whenever teacher ID is repeating itself, teacher age is also repeating. When this is unique, these two are also unique. So this dependency is valid. This is a valid functional dependency. But here what is happening? A part of a candidate key is trying to determine a non-prime attribute. Teacher age is a non-prime attribute because this is not a part of a candidate key. So teacher age is a non-prime attribute. So teacher ID is trying to determine teacher age. This is becoming a partial dependency. Understand why it is a partial dependency? Teacher ID itself is not determining anyone. That means what? Teacher ID is having repetitions here. So teacher ID is not candidate key or primary key or any key because it is having repetitions. But if you combine teacher ID with subject, then that combination is your candidate key straight away because that is a unique combination in every row. Now, if teacher ID and subject is a candidate key together, is the group, teacher ID comma subject, this group is a candidate key. But by looking at the table straight away, you can say that teacher ID is determining teacher age. Teacher age will not depend on subject, right? Teacher age will depend on teacher ID, plain and simple. So teacher ID to teacher age is a valid functional dependency in the table. This means what? Teacher ID being a part of a candidate key, not the whole candidate key, but a part of a candidate key, is trying to determine teacher age. So here it is becoming a partial dependency, and hence this particular table structure is not in 2NF. Now you can say the first criteria is it must be in 1NF. So you didn't check because 1NF is normal. You see teacher ID, subject, teacher age. 3 column names are unique. Every cell is having only one value, that is atomic. Teacher ID is having integer value, subject is having varchar value, teacher age is having integer value. So all criteria of 1NF are satisfied. But the criteria for 2NF, that is having no partial dependency, is getting violated here. So what we will do to make the table in 2NF, we will break it into T1 and T2. T1 will have teacher ID, subject, and T2 will have teacher ID and teacher age. Right? So if you break these two tables, now they are satisfying in 2NF. Like T1 is having what? 17, 17, 25 and 43, and the name of the subject corresponding like chemistry, biology, maths and English. And what your T2 is having? 17, the teacher ID with 17, this is ID, this is age, is having the age of 35. 25, teacher ID is having age of 42, and 43 ID of teacher is having age of 32. So there is no repetition, and also there is no partial dependency, right? So this is how you need to check partial dependency, and this is how you need to break the table so that you can say that this particular table is in 2NF now. So first you have to check whether the table is in 1NF or not. If it is in 1NF, because how it is in 1NF? 3 criteria for 1NF. One is all cells are atomic. You see every cell, if you draw the table, then you will find every cell is atomic. Next, all the column names are unique. Teacher ID, subject, teacher, everyone is unique. Fine. Last one, every column should have only one data type. So teacher ID is having integer data, subject is having varchar data, teacher age is having integer data. Right? So it is in 1NF. But when it comes to functional dependency, you see, teacher ID itself is not unique, so we cannot say this is a candidate key or primary key, anything. So teacher ID and subject, if you club them, then they become a candidate key. Now teacher ID, subject is the candidate key, that is fine, but teacher age, this particular column is dependent upon teacher ID. Age is obviously depending on teacher ID. Age is not dependent upon subject, right? So teacher ID is determining teacher age in this particular table, but teacher ID is a part of your candidate key. Teacher ID is a part of your candidate key, right? That means what? This teacher ID to teacher age, this is becoming a partial dependency, but that is not allowed in 2NF. So what we do, we break the total table into 2 tables, and this is your ultimate structure. So if you break this table into this structure, you will say that your table is now satisfying second normal form or 2NF. Okay. 2NF is clear to everyone. 1NF and 2NF, both are clear to everyone? One NF and 2NF, these two are clear to everyone? They're expecting some answers in the chat box. Okay, so almost all yes I have got, but just one or two queries about the partial dependency. Okay, I'm just doing it once more. Partial dependency, to find partial dependency, what you have to do? First, you find out the candidate key of your table. Now, in this particular table, only teacher ID is not your candidate key, because teacher ID is not always unique, right? If you club teacher ID and subject, this total set is a candidate key. Up to this is okay. Now you see that teacher age, this particular attribute, is depending upon the ID of the teacher. Like if you say the age of mine, and if you say the age of some other teacher XYZ, the age is dependent upon the teacher ID or the teacher name, anything. Here name is not there, so on ID. Now teacher ID is determining teacher age. Now the problem begins here. Teacher ID is a part of your candidate key. Teacher ID is not a full candidate key. It's a part of the candidate key. That means it's a prime attribute only, not a key. It is trying to determine a non-prime attribute, right? So if teacher ID is trying to determine teacher age, where teacher ID itself is not a key, but a part of a key, then this FD is named as a partial functional dependency, right? So a part of a candidate key is trying to determine any non-prime attribute. Okay, so this type of dependency is a partial dependency, and we need to remove that. Okay. Okay, next one student is asking that if 17 is not repeating itself. Second and third condition in 2NF means I am not getting your question. T1, in T1, there is no FD, as 17 has different value for different subjects. Teacher ID is determining student. That is what, teacher ID is determining subject. That is what you are asking. How can teacher ID determine a subject? Because 17, this is repeating itself, but chemistry and biology is not repeating. Right? So if not given, see, FDs are not given in this particular question. Right? FDs are not given in this particular question. So we have to assume an FD. And how we will assume? By the conditions we have learned. So if in teacher ID a value is repeating itself, in subject also the value has to repeat itself, or else we cannot say that teacher ID is determining subject. If you did not have 17, suppose you have 31, then only teacher ID becomes sole candidate key, right? Then 2NF will not occur. Second condition of 2NF, I have just repeated second condition of 2NF, that is partial dependency. If a part of a candidate key, if your candidate key is one attribute, then there is no part, no proper subset. But if your candidate key is having more than one attribute, then you can have a proper subset. So if any one of that proper subset is trying to determine a non-prime attribute present in your table, then that type of dependency is named as a partial dependency. And if partial dependency is present, like here it is present, then that partial dependency portion, you just divide it into another table. That is teacher ID to teacher age. This is your partial dependency. So you create a new table where your teacher ID and teacher age will be present, like T2. Okay. I hope 2NF is clear by now. Fine. So we can move to 3NF. Okay. So we will just move to 3NF. Now, what are the conditions of 3NF? See, from 3NF, the things are a bit problematic, like as you go on in the hierarchy. So in 3NF, third normal form. First criteria is your relation must be in 2NF. That means no partial dependency should exist. Second criteria is no transitive dependency is allowed. No transitive dependency is allowed. Right? So a relation to be in 3NF, a relation to be in 3NF, we must satisfy the criteria. First one, it should not have any partial dependency. That means the table should be in 2NF. Second criteria is there must not be any transitive dependency. That means A to B, B to C, then A to C. This type of dependency must not be present. If present, then we will break the table. Take an example and understand. There are other criteria also by which you can judge if functional dependency is given, but I'm coming to that later. If suppose a table is given, then how you will judge? Employee ID, employee name, zip code or pin code, whatever you say, state and city. This is your table structure. Suppose 22, 33, 44, 45 and 51. Randomly I have given Y, X, R, X, R. Okay. Zip code. This is your zip code for Y. Okay. And for this, suppose 4622. Randomly, I have taken some values. Now, state whenever it is 2010, suppose it is UP, UK, and MP. Any random I have taken. ABC, PQR, DEF. Some unique names I'm just taking. GHI, JKL. This is your table, right? Now you look at the table. Now I have not given these arrows to find out that there is a dependency between name and zip code. I was just trying to make you understand that what are the row orientation, right? Because they have just gone a bit down. Okay, now you look at the table and try to identify what are the dependencies. See, first employee ID. Generally, we understand by this time we have understood that IDs are your unique identifier, right? So here see employee ID is all unique. So I can just say that employee ID is my key here. You can say candidate key, you can say super key, you can say primary key, anything you can say, right? So employee ID is determining name, employee ID is determining zip code, employee ID is determining state, employee ID is determining city. Up to this is okay. There is no confusion, I believe, in this. Now you see employee ID is determining zip code. Employee ID is determining zip code, which employee is working in which area. That is determining by this FD. This is valid FD. Now you go back to the table and check zip code is determining state and city. The right hand side of your table, this side of your table is also having a determinant, that is zip code. Whenever your zip code is 2010, your state is UP. Whenever it is 0222, it is UK. When is 0188, it is India. See here. Whenever zip code is repeating itself, state is also repeating itself. Understand this. Whenever zip code is repeating itself, state is also repeating itself. This means what? This means what? I can write is determining state, right? And zip code is the zip code determining city? In this particular case, the zip code is not determining your city, because city is always unique, but zip code is having repetition. So what I can do maximum? I can just change this. If I change this, if I say change this, then zip code is also determining your city. This means what? Employee ID determining zip code determining city. So what I can say? Employee ID is indirectly determining state and city both, right? So here this becomes the transitive dependency. Here it is becoming transitive dependency. So what I can do? I will break the table into T1 and T2. T1 will have employee ID, employee name, zip code. Zip code will be present, or else I cannot determine which employee is working where. Zip code, state, city. Right? So I am breaking what? The ones that are creating problem. These two are creating problem. So I have just broken that into a new table. Okay, I hope you are understanding. This is my original table. I'm repeating the total thing once more. City is also a candidate key. City is not determining anyone. So how city is being a candidate? City is not determining anyone. So why city is a candidate key? Understand here, partial dependency. Only employee ID is my candidate key. So there is no chance of partial dependency. Partial dependency will occur when you have more than one attribute in your key. Then only partial dependency will arise. Here you have only one attribute in your key, that is employee ID. So there is no partial dependency. Employee ID cannot be broken further. If it can be broken further, then only we can identify partial dependency. It cannot be broken further. So there is no partial dependency. The table is already in 2NF. Yes, I'm repeating. So in this table, you have employee ID, employee name, employee zip code, state and city. So at a glance, you will find that employee ID is all unique. So employee ID is a key. Suppose a condition, candidate key, a primary key, or a super key, anything. It's a key. Now, it is determining name, it is determining zip code, it is determining state, it is determining city. Everyone it is determining because it is a key, it will determine everyone. Now, look at the zip code column. Zip code, whenever zip code is repeating itself, the state is also repeating itself. Whenever zip code is repeating itself, the state is also repeating itself. But whenever zip code is repeating itself, employee ID or name is not repeating itself. So zip code is not a key here. But zip code is determining state and city. That dependency can exist. Understand? Zip code is not a key of the table. But if I say zip code is determining state, then that dependency is valid. Why? Because whenever zip code is repeating itself, state is repeating itself, city is repeating itself. So zip code to state, zip code to city, that is a valid functional dependency. But zip code is not determining these employee IDs or names. So the left hand side functional dependencies are not valid, but the right hand side is valid. So if I say employee ID is determining zip code, and if I say zip code is determining state, zip code is determining city, Then employee ID is determining state and city. This means there is a partial transitive dependency. What is a transitive dependency? Whenever we go via some attribute to other attribute, that is a transitive dependency. We have learned right away. So via zip code, we are reaching to state and city. That means what? This zip code to state, zip code to city is creating a problem because they are transitive. So if they are creating a problem, let's break them. Breaking will happen how? Zip code, state and city, these are having interdependency, so they are being broken in one table. And remaining what? Employee ID and employee name, they are in another table. So why I have included zip code here? Because if I do not include zip code here, then afterwards, if you try to join the table, then how you will join? There is no foreign key. So zip code being a primary key of this table will act as a foreign key of this table. Means if I say suppose employee with employee ID 44, employee with employee ID 44 is working where? So from the first table, you can say that employee ID 44 is working in 0188 zip code, and 0188 means it is India. So that person is working in India. So we are creating that link by zip code. Okay. So this is how you need to determine the transitivity and then the dependency. Yes, the table that is given to you, it is not in transit, this is not in 3NF. This table is not in 3NF because zip code is creating the problem. So I have divided the zip code into another table, and the tables that we are getting, the last tables that we are getting, these are in 3NF. There is no partial dependency. Employee ID is directly determining name, directly determining zip code. Zip code is directly determining state and city. So there is no transitive dependency. Okay. This is one rule, that is, if the table is given to you, then how you can determine whether it is in 3NF or not. Now suppose the table is not given to you. Suppose it is given like this. Relation R having these attributes, and suppose this is given and you have to check whether your table is in 3NF or not. How you can check that? First, you determine what is the candidate key. See here, A plus. How we will check candidate keys? We have done in the last class. We will be checking it by taking attribute closure, right? So A closure is ABC, B is determining D, and this is determining D. So R. So candidate key is R, comma, BC. Okay, likewise you can determine. So I already know, so I'm just writing my candidate keys are A, comma, BC, comma, CD, comma, E. These are my 4 candidate keys possible. Now how will I check? A table to be in 3NF. A table to be in 3NF for every dependency X to Y, X has to be a super key and Y has to be a prime attribute. X has to be a super key or Y has to be a prime attribute. So see, these 4 are my valid functional dependencies given. So is A a super key? Yes, A is a candidate key. That means obviously A is a super key. And B and C both are prime attribute. What is a prime attribute? Prime attribute means a part of your candidate key. So what are my prime attributes? A, B, C, D, E. Right? A, B, C, D, E. All are prime attributes. Now next one. So this is valid. CD to E. CD is a candidate key. Yes. So CD, that means it's a super key also. So E is a prime attribute. Fine. B to D. See, B is not a super key, but B is a prime attribute. So this is also valid. E to A. E is a super key because it is a candidate key, and A is a prime attribute. A is a prime attribute. So all four are valid. That means this table with this set of functional dependency are in 3NF. So how to check if only functional dependency is given, then how to check whether the table is in 3NF or not? How to check? Either your left hand side is a super key and your right hand side must be a prime attribute. If yes, then only you can obtain for 3NF. Okay. So this is how you need to check 1NF, 2NF and 3NF. Fine. Next, I will just take a 5 minutes of break and then we will explain so that you can just assimilate with all this, and then we will start with 3.5 NF, that is BCNF, 4NF and decomposition, and then we will do some problems. Okay, so I'll just take a 5 minutes break. Do not leave the meeting or else your attendance will get hampered. So those who are in the meeting, be in the meeting. We'll just meet at 10:35.
Recording stopped. Recording in progress.
Okay, so I have got one query that in 2NF, A to C is creating a problem, then why we are keeping them in the same table. Now you understand what is actually creating problem. See, the teacher ID and the subject both together is a candidate key. Okay. Now, if teacher ID is determining age in the table, teacher ID is determining age. That means what? When I have teacher ID, subject and teacher age together in a table, but teacher ID solely it is not a candidate key. Solely it is not a candidate key. It is a part of a candidate key which is trying to determining teacher age. And then we are breaking teacher ID and teacher age together. Now in this particular table, in T2 table, teacher ID is your key and teacher age is dependent on teacher ID. In this particular table, the existence of subject is not present. So teacher ID is the sole key and that is determining teacher age. So there is no problem. Here in T2 table, there is no chance of partial dependency. Understand, partial dependency will happen when you have more than one attribute to be a part of a key. If you have more than one attribute as a part of a key, then only you can break one and then that can determine someone so that partial can arise. But in T2 table, teacher ID is the sole key and teacher age, see here, teacher ID is unique and teacher age is something. So teacher ID is determined teacher age, right? So it is a direct dependency. There is nothing partial. In the main table, it was partial. But as soon as you are breaking it, it is not becoming partial. Okay, is it clear? Fine. Now next we will move to the stricter version of 3NF. What is that? We call it as, there are different names. We call it as BCNF. We call it as 3.5NF. Thing is same. What is it? In 3NF, we were checking both the left and the right hand side, right? So either your left hand side will be a super key and your right hand side will be a prime attribute. But in your BCNF, there is only one condition. That is, your left hand side of every functional dependency, the LHS of every functional dependency is a super key. The LHS of every functional dependency is a super key. So that is the advanced version of 3NF. Okay. So what happens here? What happens in BCNF? All the functional dependencies X to Y that will be given to you, all X should be super key. Right hand side, whatever it may be, but left hand side, we have to find out that there is a super key. Okay, and generally all the tables that we maintain in our database management system, everyone's left hand side is a super key. I'm not saying candidate key or primary key, but a general super key. Okay, that means a determinant. Okay, now see, take an example. Suppose employee ID, country, department, department type, department number, right? All 3NF relations are not in this. No, Every 3NF is not in BCNF, because in 3NF we are checking the right hand side as well. But in BCNF, we are checking only left hand side. All tables which are in BCNF must be in 3NF. But every table that is in 3NF cannot be in BCNF. Okay, BCNF is a higher version, it's a stricter version. Fine. Now see, suppose we create a table. Suppose 26 both 36 and 35. Yeah. Development, testing, storage, designing. Department type, three 300. Okay. Now you see, this is 26. Now see from the table, employee ID is determining country, because whenever employee ID is repeating itself, country is also repeating itself, right? Department is determining department type and department number, right? So only employee ID cannot be a key here. Only how you will check, I will come to that later. First, you understand that if a table is given, what you need to check. What are the steps? I will come to that later when we do exercise. Okay. Employee ID itself, it is not a key because it has got some repetition. And employee ID is not determining department. Employee ID is not determining department type. Employee ID is having 26 and it is not constant here. So it is not determining. So what we can say, my candidate key is employee ID, comma department. And this is your super key as well. This is your super key as well. Super key and candidate key is what? Super key is something which is determining other attributes. And candidate key is, if you are minimizing the super key, that is the minimum one. That is the candidate key, right? So employee ID itself is not a key. Department itself is also not a key because department cannot identify employee ID, right? By common sense. In a department, like one department can have multiple employees, right? So department cannot identify, but if I combine employee ID and department, that can be a key. Now see, what is your condition of a BCNF? Every functional dependency X to Y, X has to be a super key, right? So this is a valid dependency, this is a valid dependency. But is this a super key or is this a super key? Alone, they are not super keys. They are a part of a super key, right? So how we can break this? Understand why this is not in BCNF. These two, this employee ID to country is an identified functional dependency, valid. And department to department type, department number, this is also valid functional dependency we have identified from the table. But when we check for super key or candidate key, we are finding that employee ID or department itself, they are not any key, they are not super keys. So we can identify employee ID plus department together, that can be a candidate key or a super key, right? So if I have these two as valid functional dependencies and this as my candidate key or super key, then this particular table is not in BCNF. So how to break it? How to break it? The problem creators will be separated, right? So the first table will be employee ID with their country. That's it, right? First problem creator, this was not allowed because employee ID is not a super key in this table. So let us break it. Next one, department with department type and department code or department number, whatever you call it. These two are my problem creators, so I have broken them. Now you see employee ID and department. These two are also dependent on each other. Employee ID and dependent, these two are also depending on each other. With employee ID, I can find out that in which department that person is working. So what can I say? I will make another table with the last problem creator, that is employee ID with my department. Right? So when you try to again join them, you map table 1 to table 3, then table 3 to table 2. So employee ID here, employee ID with department here, and department here. Okay, so this is how you need to join. So not only breaking is the one where you need to concentrate, but after breaking, when you join back, there also you should have the provision to join back. So how you are doing it? Understand your mother table. Employee ID, country, department, department type, department number. Fine. Employee ID is having repetition. These are the repetition. Country is also repeating itself. Fine. Next, whenever employee ID is repeating itself, country is repeating itself. So employee ID to country is a valid functional dependency. Fine. Next, employee ID is not directly determining department, because whenever employee ID is repeating itself, see, departments are different, right? So what you can say here, employee ID is only determining country. Next, if I say department is determining department type and department number, that is possible. Department is determining department type, department number, that is possible. Department is all unique, right? So it is determining department type and department number. So I have got two valid functional dependencies. 1, 2, right? There is no problem. Now you try to identify a key from the table. That can be a super key, that can be a candidate key, anything. So this particular candidate key or super key, whatever you call, only employee ID cannot be a super key here, because employee ID is having repetition. So it cannot be a super key. Employee ID plus department, if you just club those two attributes together, then you are finding a key. Okay, then you are finding a key. There is no problem. But if this is your situation and a table to be in BCNF, your all left hand side of all FDs must be a super key. But if your super key is employee ID plus department, then the valid functional dependencies in the table, they are not satisfying the left hand side criteria. So now I have to break my table. How I will break? The problem creators will be broken. So the first problem creator is employee ID to country. So I have made a table employee ID and country. Now here, employee ID to country, employee ID is my super key, that is determining country. So this table is in BCNF. Next, department to department type, department number, department to department type, department number. Here department is my candidate key, so no problem. Next, employee ID and department, these two are a combination. So employee ID and department, I have made another table. Why? Now you can ask that how you have made this table. Now see, you are breaking the tables, but afterwards you need to join them back. So how you will join them? Employee ID to table number 3 is employee ID. Where you find the department, then you join the department with table number 2. So number 1 table, natural join, number 3 table, natural join, number 2 table. Or if you do normal join, then T1 dot employee ID equals to T3 dot employee ID. Join T3 dot department to T2 dot department. Okay, so not only breaking you will consider, after breaking if you need to join them back, then how you will determine that joining, that also you have to determine. Okay, so what is BCNF? Any table, a set of functional dependencies given, you will check for all functional dependencies. Your left hand side must be a key. We say super key, but it must be a key. A super key is what your candidate key is all about, right? So left hand side must be a key. And why it is a stricter version of 3NF? Because in 3NF we had a scope of checking right hand side as well, but in BCNF we don't have that scope. Okay, so this is your BCNF. Fine. How T3 is in 3NF? T3 employee ID to department, only one dependency, employee ID to department. So there is no transitive dependency, only 2 attributes. So it is in 3NF, obviously. All values of employee ID are unique, then employee ID can be a super key. Yes, if all values of employee ID are unique, then there was no problem. Employee ID to country itself is a key, means a super key to a non-prime attribute. Right? So this is BCNF. Now last we will learn 4NF. We have already learned multi-valued dependency, right? So a table to be in 4NF, please understand BCNF and 3.5NF are same. Okay. 4NF, number 1, it must satisfy BCNF, and number 2, there will not be any multi-valued dependency. There will not be any multi-valued dependency. Let us take an example. Student ID, course, hobby. Very, very common example you will find in books and other places. So understand this. Suppose this is a random table, okay? Student ID, course, hobby. Now you see, student ID 21 is having multiple courses, multiple hobbies, right? So from this, it is clear that student ID is having multiple dependencies. It is having multi-valued dependency on course. Student ID is having multi-valued dependencies on hobby. Why? Now you can ask why. Why I have explained earlier also. For one particular student, if I have more than one courses, more than one hobbies, then obviously they are multi-valued, right? Suppose this 34, this student is also 34, and this student is again having multiple hobbies, right? Multiple courses. That means one student is having multiple courses, multiple hobbies. That means that is a multi-value dependency. For one attribute, student ID, I am getting multiple values in course column, multiple values in hobby column, right? So it is a multi-value dependency. If there is multi-value dependency, then this particular table is not in 4NF. So how to do it? How to break it into multi-value to get rid of multi-value dependency? Create two tables. Those who are creating problem, we are breaking them, right? So course with student becomes one table and hobby with student becomes another table. Very simple. Okay, how to check multi-value dependency? There must be at least 3 attributes. Any one of the 3 attributes must be the determinant, and other 2 attributes must be independent of each other. Like course and hobby, they don't have any link, but student ID is determining course, student ID is determining hobby, right? So in this particular scenario, who is creating problem? The student is creating problem, student ID, because it is having multiple dependencies. So we are just breaking them. Student ID to course, student ID to hobby. Okay. This is 4NF. Again, if you want to check for BCNF, this table is obviously in BCNF because student ID here is the determinant. Student ID, or based on student ID only you are determining course and hobby, right? So here it must be in BCNF. Generally, when we check for 4NF, we check for only MVD. We do not check for the lower grades of normalization. We generally go for the MVD. Okay. Now we will do a problem. Like what type of problems you will get. Let us take an example. Question, suppose you are having R. The FD set, the valid FD set given as okay. There are few steps. Step 1 is determine all possible candidate keys for R. What is the answer? Tell me. Do it and tell me what is the possible answer for first step. What is the candidate key for R? How to check candidate key? How to find out candidate keys? First, I have to check the essential attribute. Any attribute who is not on my right hand side. What is that? A and C are my essential attributes. Again, I say, if you do not study the previous classes lessons, you will not be able to catch up. So A and C are your essential attribute. A closure or C closure will not be able to determine R because individually they cannot determine. Everyone should be present. So AC is equals to ACBE and BC is determining D. So it is equals to R. So AC is a candidate key, right? Now, if any more candidate keys are present or not, how you will determine? See, whatever candidate key you will have, that must have at least AC in it, because essential attributes cannot be determined by anyone else. So at least AC must be there. Fine. Now, you can add on variables on AC, right? Like you can do ACB, you can do ACD, you can do ACDE, or so on. But these will be the super keys. They will not be the candidate key. So only one candidate key possible, that is AC. Only one candidate key possible, that is AC. right? Up to this is clear to everyone. Why not any other candidate keys? Because A and C, they are my essential attributes. So they must be a part of your key. Okay. Now, if they are a part of a key, then only they can determine R. Yes, they can determine R. I have proved that. Now, if you add on more variables on AC, they will be super keys. But the minimum version is your candidate key. That means AC is your candidate key. No other candidate key is possible. Okay. Next, how step number 2. This is your step number 1. You have determined the number of candidate keys. Here only one is possible. Step number 2. Identify prime attribute and non-prime attribute. So what is your prime attribute here? A, C. What is your non-prime attribute? B, D, E. Fine. Prime attribute is A and C. Non-prime attribute is B, D, and E. Okay. Identifying these. Now step 3. Checking for normal forms. Checking for normal forms. So we will start with, see, whatever tables are given, if only functional dependency is given, you cannot check 1NF. I have already told. So we will check, consider the table is in 1NF already. Because table structure is not given, so we cannot determine. Only dependencies are given. So we will start checking from 2NF. Okay. So I am checking for 2NF now. What are my dependencies? BC to D, AC to BE, and B to E. We have to check what? Partial dependency. We have to check 2NF. So we have to check partial dependency. Partial dependency means what? Any proper subset of AC is trying to determine anyone else or not. See, BC is determining D. Fine. There is no problem because BC is not a proper subset of AC. AC is determining BE. AC together is determining BE. There is no problem. And B determining E. There is no problem because B is not a proper subset of AC. So my table is in 2NF. Done. Next, I will check for 3NF. I will check for 3NF. 3NF, how I will check? For every X to Y, X has to be a super key or Y has to be a prime attribute, right? So let us check by one. BC. BC is not a super key. BC is not a super key, right? So D is a prime attribute. No, D is a non-prime attribute. See, D is a non-prime attribute. That means what? In my first FD only 3NF fails. In my first FD 3NF fails. Neither my BC is a super key nor my D is a prime attribute. That means what? In the first FD only my 3NF fails. So what I will say? That 3NF is not satisfied. The relation, the FDs of 3NF is not satisfied. So my table R is in 2NF. This is my answer. My table R is in 2NF. Suppose 3NF is satisfied. Suppose in some case 3NF is satisfied. In that case, we will go for 3.5NF. Then we will go for 4NF. Okay, generally we do it up to 3.5NF, that is BCNF. But if you know 4NF, then you can do it. Okay, yes, I'm repeating 2NF. 2NF means what? Any proper subset of AC is trying to determine any other variable, any other attribute, right? So AC's parts are what? A and C. Individually A and C is determining anyone. In this FD set is A or C? Anyone individually is determining anyone? No, right? That means what? There is no partial dependency, so the table is in 2NF. Okay. Is it okay? Can you repeat 4NF? Yes, I can repeat 4NF. 4NF, how you will judge? See, for one student ID, you are having multiple values of courses, multiple different values of hobbies. That means what? One student ID is having multiple course, multiple hobby. That is a multi-valued dependency. If this dependency is existing, then you have to break the table. How you will break? The number of multi-valued dependencies present, you break everyone. Okay? So this is how you can check for the dependencies. For this question, 3NF means how it is not in 3NF. In 3NF, what is the criteria? For every functional dependency, either your left hand side is a super key or your right hand side is a prime attribute, right? So if you look at the first FD, anyone for every FD, that means if anyone fails, that means your table is not in 3NF. So BC to D, BC is a super key. No. D is a prime attribute. No. AC, A and C are prime attributes. D is not a prime attribute. So neither my left hand side is a super key nor my right hand side is a prime attribute. So 3NF fails. Okay. I have a PPT and I will show it right now and I will give that PPT as notes. Other notes I don't have. Before that, we will do another problem. I'm just giving you another problem. You first do it and tell me in what normal form it is. Wait, I'm giving you one problem. Okay, I'll just write it because if I say, you may not follow. I'll just write the problem, you solve it for me and tell me. Question 2. The FD set is B to A to C, BC to D, AC to BE. Tell me what is the highest normal form satisfied here. What is the highest normal form satisfied here? I hope the question is clear. Table having attributes A, B, C, D, E, and the functional dependency, valid functional dependency set is given B to A to C, BC to D, AC to BE. Okay. So start with step 1. First tell me, step by step, you will tell me the answer. Solve and tell me what are the candidate keys. What are the candidate keys? I have got only one answer. Tell me what are the candidate keys? Is there any essential attribute? Is there any essential attribute in the table? Yes or no? There is no essential attribute, right? That means what? One by one, I have to check. First, you check A plus, then you check B plus, then you check C plus, like that. And tell me what are the candidate keys. BE is not the candidate key. One student is saying BE is the candidate key. No, I have already got correct answers. Excuse me. But BE is not the candidate key. Anything else? A is a candidate key and B is a candidate key, okay? Those who are saying C, only C can determine anyone? I don't think so. Only D can determine anyone? No, D is not even on the left hand side. And if B is a candidate key, then BC cannot be a candidate key. BC can be a super key. BC cannot be a candidate key. For those who are saying BC, those who are saying AC, A and B are candidate keys. If A and B are proved to be candidate keys, then BC, AC, they cannot be candidate keys, right? Done. Next, step number 2. Identify the prime attributes and non-prime attribute. So prime attributes are A and B and non-prime attributes are C, D and E. Right? Next, you consider that it is already in 1NF. Fine. Is it in 2NF? Say yes or no. Is it in 2NF? Say yes or no. Is this relation is in 2NF? Is there any partial dependency present? Is it in 2NF? Yes or no? I have got only one answer correct. It is not in 2NF. Few students are saying it is not in 2NF. What is 2NF? If any proper subset of a candidate key is trying to determine any non-prime attribute, here your candidate key is A and B, not AB together. Please understand, you are making mistake. AB together is not a candidate key, only A and only B. So the students who are thinking B to A is a partial dependency, it is not correct because B itself is a key, A itself is a key. Right? So there is no partial dependency. The table is already in 2NF. Right? There cannot be any proper subset of A or B. Proper subset will be null. Because A and B, they are itself one attribute key. They cannot be broken further. Right? So it is in 2NF. Is it clear? B itself is a key. So if B is determining someone, then there is no problem. Okay. Now you check for 3NF. Is the table in 3NF? Is there any transitive dependency? Is there any transitive dependency? Is the table in 3NF? Yes, prime attributes are present. A or B, they are prime attributes. They are keys, so they have to be prime attributes. Left hand side has to be super. See, the students who are saying it is not in 3NF, please understand, left hand side has to be super key or right hand side has to be prime attribute. So left hand side is a super key. B and A, they are candidate keys. That means they are super key. And BC is a super key. That is not a candidate key, but it is a super key. BC means what? If B is present, that means it is a super key. AC is a super key. So all left hand sides are super key. That means it is 3NF as well as it is BCNF. Understand? It is 3NF as well as it is BCNF. Right? Because every left hand side is a super key. Why it is BCNF? Because every left hand side is already a super key. That means it has to be in 3NF and it is already in BCNF. Right? All the FDs present, 4 FDs, everyone's left hand side is a super key. Right? Is it clear why it is in BCNF? Every left hand side is a super key, so it has to be in BCNF. বুঝতে পারছো? Is it clear why is it in BCNF? Not getting any answers. Yes, B determines A and A determines C. This looks to be transitive, but B and A both are candidate keys. Both are candidate keys. That means left hand side are super keys as well as candidate keys. So it has to be in 3NF. Okay, now if you have already proved that it is in BCNF, right? Now what about 4NF? Can you judge 4NF? See, no multivalued attributes are given, no multivalued dependencies are given. So you can say it is in 4NF, but to judge 4NF, we need the table as well. So generally when these type of questions are given and it is asked that what is the highest normal form, we generally go up to BCNF. 4NF, we generally do not do until and unless the table is given. So here the table is not given, so we will not judge for 4NF. Okay. So we will not go till 4NF, we will just consider it up to BCNF. Yes, there is 5NF, but 5NF is not much required. Okay, there is 5NF, but 5th normal form is not required. Okay. Though if you want, I'll just tell you that like what is a 5NF or how to determine 5NF. Why not 2NF? Please repeat. 2. It is already present in 2NF. Why not means it is already present. So there is no question of 5NF. See, for 5NF, we require the concept of lossless decomposition. So for that thing, I don't think today it is possible. So lossless decomposition is present in your syllabus, and like not only syllabus, questions are also asked. So another day we will do lossless decomposition, and then in relation to that we will go to 5NF. So a table to be in 5NF, the first criteria is it should be in 4NF, and the table means the breaking of the table will have no loss in decomposition. So that the decomposition must be lossless. So what is lossless decomposition? That we will discuss another day, because today already you must be overburdened with all these NFs because you are learning it or for the first time, maybe for some people, and for some you are just repeating it many days after. So today I'll not go into lossless decomposition because I have to solve one problem and show it to you. That is not possible today. So normalization, we will stop up to 4NF today. Next day or next to next day, we will do 5NF. Okay, so for 5NF, a table to be in 5NF, it has to be in 4NF, and there should be lossless decomposition. Decomposition means you are breaking the tables, right? So this breaking of the table should be lossless in nature. Fine. So that is all for normalization. Okay, so one thing I will do, I will just show you one PPT. Means showing that PPT may not help you, but I will just give you for your reference. See here in this particular PPT, I have just jotted some examples, anomalies I have given. See, up to now, whatever I have done it by writing, right? So that you can also write and understand by solving. But this PPT has got everything, that what are the anomalies, insertion anomaly, update anomaly, deletion anomaly. Then I'm going to normalization, that is what is the use of keys in normalization. First normal form, all the criteria are given. Second normal form criteria given. Third normal form criteria given. BCNF criteria given. 4NF and multi-value dependency explained. Okay, in a nutshell, it is given in the slide. Next, examples are given. Like you can see for 1NF atomic values, OS and computer network, C and C++, these are multiple values in a single cell, right? So this is not allowed, so it is broken. Next, 2NF, here you can see student ID and subject ID is determining the candidate's marks, suppose, right? But subject ID is also determining marks. So here you can see the partial dependency is present. So things are explained here. 3NF example is given, transitive dependency. So in this particular PPT, everything is given in a nutshell, right? So I will just give the PPT so that you can just do a bit of practice, okay? Now again, what I had planned was I will just share the SQL part with you. I'll start with the SQL, but SQL PPTs showing that those PPTs, I don't think there is that not that much time. And also you must be overburdened already. So what I will do is I will just open the MySQL prompt and I will show you how to work, okay, how to set path, just the basics, so that next day we can start with SQL. I hope you can see the screen. Can you see the screen? I'm not sure whether you can see the screen. Yes, okay. Okay, so to practice SQL, as you have already done relational algebra, so SQL we will do it very fast, right? So like I will just show the PPT within half an hour next day, and then I will show you how to work, right? Means difference between different table joinings like inner join, cross join, and natural join. What are the difference? In which cases we are using outer joins? How to modify a particular table? What are the aspects which you can modify in a table, right? Suppose the aggregate functions like maximum, minimum, average, round off, those things. How to display the date of the system, those things, okay? But today I'll not go into that much details. I will first show you that in a command prompt, like every one of you are having command prompt. So if you install MySQL, you have to first install a local host. Okay. So I have already turned my XAMPP server on. I am using XAMPP. So I'm using XAMPP server. I have already turned it on. You can use Tomcat, or you can use like if you are using JDBC, then you have to go for a better local host. But as I'm doing only MySQL, I can go for XAMPP. Okay. So what I will do first, I will set the path. I will first go to MySQL server. Fine. So I have gone to C, so I already know what is my path. Okay, now you have to identify what is your path from your computer. Fine, so I know that within program files, I have my MySQL path. So you have already done operating system. So with command prompt, you must be having some idea on command prompt. I just believe that. Even if you don't have, please revise that before you come to the next class. Okay. Then I go to my MySQL folder. Right. So within the folder, I have my so MySQL server. So exact name I cannot remember. So what I will do, I will just MySQL server and tab. If I press tab, the name of the server will come. Okay. Online IDs are also available. Like also you can do it on Oracle also. Not only MySQL, you can do it on Oracle also. Like see, when they are asking you for queries, basic query remains same. Right, some are the case sensitive ones, some are the case insensitive ones, some require semicolon, some do not, but the overall query remains same. Like for inner join, you have to write the dot operator you have to use, and for cross join you don't need anywhere. For natural join you don't need anything. That syntax remains more or less same, but the, like I can say punctuations or something like that, those things vary. Because you can use any IDE of your choice. You can, yes, you can use PHP MyAdmin, same thing. Okay, so let us just enter, and then I have to go to my bin. I'm just setting path. So according to your system, you will set your path. Then MySQL -u means the user. I am using root. I don't have any password. If you have password, you will write -p, then your password. Okay, even if you don't write -p, they will prompt you for your password. Okay, so you can see my MySQL prompt is already there. Fine. Yes, I will explain join. Means I will not explain, I will run queries and you will see that how the joins are different from each other. Like three things: inner join. Inner join means intersection, but for inner join you have to use the dot operators in table, like table name dot the column name, right? For cross join, you don't require any operators. Cross joins are just like Cartesian product. So every row of one table will get multiplied to another, all rows of the other table. Okay, and for natural join, you have to just use the keyword natural space join. You don't require any operator. Okay, if the column names are matching, then natural join will automatically occur. And for outer join, again, you have to specify by dot operator. Again, in MySQL, we don't have the provision of full outer join, but left outer join and right outer joins are present. Okay, I will repeat as I will proceed in doing the queries, I will repeat the concepts. And as you see the output, you will also understand how the difference is going on. Okay. Then once you get the MySQL prompt, then you can just understand, or suppose what databases are already made. What databases are already made, you can just use that by show. You can see these databases are already made. So I have already taken PPT classes of previous batches. So these databases are already made. Suppose movie is one something very interesting. So if I want to use movie, so how I will do, use the name of the database changed. You can see the output, database change. That means it is already inside the movie. Now if I do show tables, so what are the tables in movie that is already showing? So something that is already made, you can just utilize it. Okay, something that is already made, you can just utilize it. Fine. Next, suppose you want to see that what is there in actor. So very simple query. See here, these are already present in actor. Okay. Suppose in movie, here you cannot give database name. Here you will give the table name because already you are inside some database and you are working on a table. Suppose if I give some file name, you are giving some like some table name, you are giving student, that is not present in your movie. In your movie, what you have? In your movie, what tables do you have? Actor, director, movie cast, movie direction, and in that you are trying to find student. Student is not present, so that is just giving you an error. Movie dot student is not existing, right? So suppose select movie cast. So here you can see your actor is having actor ID, movie is having movie ID, and it is movie cast is joining them by actor ID and movie ID, right? So you can just do it like this. If you write it like this, suppose actor. What is your desired output? Which actor is working on which movie, right? But if you write just this, see here, all actors are joined to all movie IDs. That is not required. That is not desired. So, see here, only which actors are working in which movie, that is only shown. So this is how I will show you next day that how your how your tables are getting joined to one another. What is the difference? You can see if you write just join, the keyword join, and if you write the keyword natural join, what is the difference? You can see here. If you write only join, or if you write cross join, let me write. If you write cross join, what will happen? See, cross join and join are same. If you write cross join keyword, it is Cartesian product. If you write join keyword, it is Cartesian product. But if you write natural join, then it is a something that is meaningful. Which actor is working on which movie, right? Again, if you write if you write inner join without any constraint, then it results in a Cartesian product. Okay. If you write movie on movie cast dot act, then you see it is behaving like natural join. So inner join with criteria is natural join. Inner join without criteria, without the matching criteria is cross join or normal join. Okay, so this is an overview that I am trying to give you, that how to set your path, how to check your database. Suppose you want to go to another database. See what other databases are available. PPT class. Suppose PPT underscore class. So I'm just going to my MySQL prompt. You can clear the screen. I'm not just doing it. Database changed. For student age. Okay. Upper arrow will lead you to the, sorry. This is the student table. This is the course table. And some student age table was also there. I don't know. I don't remember. Due to some problem statement explanation, I may have made this. Okay, due to this minus I have made. So these are some random things. So I will explain the aggregate functions, these joins, these things next day. So what I will do is I'm planning. I'll just go through the PPT once. I have one PPT. So I'm just closing it. The MySQL portions PPT that we have, that I will just explain in half an hour or so, not today, next day, and I will then explain. So I have one basic comment query, PPT, and one subquery PPT. So there are many things. Subqueries are again important. Subqueries also you require. So this is your PPT where you have comments. Right. So database creation, new database, show database, use database, then drop database. Then within a database, if you enter, you want to create a table, then create new table. This is the syntax. In bracket, you will give everything, the column name, the data type of the column. What you can do is, I can post this PPT also so that you can just relate while you will proceed. Right. So again, we will take describe table means the structure of the table will shown. Select star means what? The structure means the schema along with the data, everything is shown. But if I do just describe the table name, then only the schema of the table will be shown, and what integer data, varchar data, what type of data is present, that is shown. Okay. Again, alter table, different things, multiple columns, how you can add, modifying table, dropping table, renaming of columns or in a table, or renaming of the table, everything is present. So today I will not go into details because again it may create a bit of problem for you, because already you have done problems on the normal forms. So now what I will do is, I will just give you a bit of problem on the normal forms so that you can solve and tell me in what normal form they are. Okay. One or two problems, just not much. Quickly just tell me what is the highest normal form for this one, R1 and R2. For both the tables, tell me the highest normal form. Write the answer in the chat box like this. R1 dash NF, like dash you have to fill. Okay. So just tell me. I'm waiting for your answers so that we can end the class with a success. Just tell me what is the R values, what are the normal forms? Okay, so as I'm getting some answers, R1. I'm explaining for R1. In R1, we have A and C as our essential attributes, right? Because both are not present in our right hand side. Now, alone A cannot judge A, B, and C. Alone C cannot judge A, B, and C, right? So A and C has to be together. So AC becomes my candidate key, only candidate key. But as you can see, a part of AC, that is either A or C, is again determining B. So a part of my candidate key is trying to determine a non-prime attribute, that is B. That means it is having partial dependency. R1 is having partial dependency. So R1 is not into NF. That means R1 is in 1 NF. R1 is in 1 NF. Clear? R1 is in 1 NF. Is it clear? Yes, I'm coming to R2 first. Let us understand R1 because some people were writing R1 is in BCNF. Okay, now see R2. In R2, you have A as your essential attribute, B as your essential attribute. So alone A, if you do it A closure, can it determine ABCD? No. A and D both must be present. So AD, if A and D both together is my candidate key, then alone A is determining BC. That is a partial dependency. AD is my candidate key in R2 table. AD is my candidate key. A part of AD, that is A, is determining BC non-prime attributes. That means what? Partial dependency exists. So R2 is also not in 2 NF. That means R2 is also in 1 NF. Clear? If it is not in 2 NF, there is no question of going up in 3 NF, 4 NF, nothing. Right? So R1 and R2 both are in 1 NF. Is it clear to everyone? Is it clear to everyone? R1 and R2 both are in 1 NF. First, you determine candidate key. Then you find out whether any part of the candidate key, yes, R2, I'm repeating, R2, A and D both are not in your right hand side. That means they are essential attribute. So AD is your candidate key. A is a part of AD that is trying to determine BC. So a part of a candidate key is trying to determine non-prime attribute. That means what? Is a partial dependency. So if partial dependency is present, that means it is not in 2 NF. That means what? It is in 1 NF. So it is in 1 NF. Okay? Okay. So today I'll end the class here. I'll post some of the PPTs that are required and I'll try to post some problems as well. Let us see how much I can. And next class, we will start with SQL directly. Okay, okay. One more thing that is left, that is lossless decomposition. I will do that. 5NF, I will just explain and then we will go to, what do you call, MySQL, okay? Yes, in R1, AC was the candidate key. Okay, so I'm just ending the session here. Thank you for attending. See you in the next class.